Hello, this is a video in which we will talk about two-sample testing in JMP, specifically testing where we have two independent samples, one from each population that we wish to compare. And in this video, we will talk about the two-sample t-test. There are two versions, one assuming the two populations have equal variance and the other assuming the two populations have a different variance. We'll also talk about two-sample equivalence testing and also talk about the way we test for equal variances. The materials relate to the statistical testing 2 notes, and the contents of these videos are contained within those notes. And we're going to begin by talking about two-sample t-tests, and I'm mostly going to talk through the issue using JMP. And here we're using the aluminum lithium or AL_LI data. And I'm going to go ahead and use a JMP data table to talk through two-sample testing. So in this particular case, we have 80 measurements of breaking strength for samples of this aluminum lithium material. And the tests were done in two different laboratories or test sites, and we're interested in knowing whether or not there might be a bias or a mean difference between the two sites. So the two-sample t-test tests for a mean difference between two populations. So we want to compare the overall average for test site 1 to test site 2 to see if there might be a difference. So I'm going to go and jump to the Analyze menu, go to Fit Y by X because I want to compare two populations, and that means I want to compare two columns. I want to compare KSI, the response, to test site, which we refer to as X, which defines the two groups. So in the Fit Y by X launch window, KSI is the response, test site is X. Once the report window appears, we can see from the scatter plot that the overall scatter, if you just look at the overall scatter, in the measurements for both groups is very similar. This visually tells me that there's really no issue with assuming that both populations have the same underlying theoretical variance. Therefore, the two-sample t-test, assuming equal variances, is appropriate. Later, we'll test this concept. And why the equal variances assumption is nice, it actually gives you more degrees of freedom to estimate the common variance between the two groups. If we assume both groups have the same variance, why not pull the data together from each group and come up with one overall better estimate of that variance? So to do a two-sample t-test, assuming equal variance, go to the report menu to the left of one way, click, and select the second option, means ANOVA pooled t. Pooled t is the test that assumes both populations have the same theoretical variance. Okay? So we perform the test. Notice that JMP has given us means diamonds in our display. What the means diamonds are basically visual confidence interval. The vertical tips are 95% confidence intervals for the true theoretical mean for each group. The vertical distance, as I said, is the confidence interval. A horizontal line bisects the diamond, and that is the sample average. Given both of these intervals almost completely overlap, it's entirely plausible that both groups have the same theoretical mean, i.e. there's no bias. And down below in the means one-way ANOVA report, we are given these confidence intervals, and you can see they greatly overlap. But we're also given a two-sample t-test report, and notice it says assuming equal variance, and we simply look for the p-value for our test, which is about 0.7, which is very large, indicating we have little evidence that there is a bias between the two test sites or populations. And if we take a look at the confidence interval, notice that 0 falls almost in the middle, meaning it's entirely possible that 0 is a reasonable value for the overall mean. And if you're interested, I'll just quickly show you what the overall hypothesis would be. So the null hypothesis, we'll call it H naught, is simply mu1, the mean of test site 1, equals the mean of test site 2. This is the two-sample test, the only one we're going to deal with. And then, of course, the alternative is very simple, and that is mu1 is not equal to mu2. So given the very large p-value and also looking at the confidence interval, we really cannot assume that there's an actual difference between the two groups. So at this point, we cannot say that there is a significant bias between the groups. Okay, so that's the two-sample t-test. While I'm in here, if you want to do the test for equal variances, you can go down to, in the main report menu, next to the left of one way, go to the Unequal Variances test, and I'll recommend you use the Levine test. This has been heavily studied in simulations and found to be the most robust and powerful of the equal variance tests. Notice for the Levine test that the p-value is also large, indicating there is really no evidence that the two groups have a different variance. Therefore, we would proceed to assume both groups have an equal variance. Now, if you still want to go ahead and perform the unequal variances test, go to the main report menu, again, click on the red arrow, and select the option t-test. Now, the mathematics of the unequal variances test are somewhat difficult. We won't cover them. You can easily find them online if you wanted to Google it, but generally what I find is both tests generally give you exactly the same result. So we have exactly the same conclusion in the unequal variances test, that there's no real difference between the two groups. And then finally, you can do two-sample equivalence testing. In other words, remember equivalence testing we covered in the one-sample case. What we're saying is we will assume the two groups are exactly equal in the mean, in this case the two test sites, as long as the mean difference lies within some window. In this case, the engineers have decided that as long as any potential bias between the two test sites is between plus or minus 15 KSI, they will assume that they are equivalent or equal. So I click on Equivalence Test. The difference considered practically zero, meaning it's of no interest, is 15. Click OK. And just as we did in the one sample case, we assume equivalence if both of our one-sided hypotheses reject. And we can show you in the two-sample testing notes, which you should read. We'll just go ahead and click ahead, and you can see that both groups are considered equivalent if we reject both of the null hypotheses, which we are going to do, and we assume that whatever the bias is, it's somewhere between minus 15 and plus 15. That is, we have accepted the two alternative hypotheses. And there are many, many other types of two-sample inference, but what we have